So I'm just going to talk for 15 minutes about a very small part of the work of Rahul. Rahul works mainly in the subject of Gromov-Witten theory. So I'm going to tell you a little about what that is. But I'll start a bit before that. So, people are familiar with lines in the plane, so I can parameterize them by three real numbers, A, B, and C. And now I could scale them all equally. That wouldn't change the line, the zeros of that linear polynomial. So I have two parameters, so I might have some two-dimensional family of lines. So I might want to impose two conditions. I would expect some finite number of solutions, some finite number of lines satisfying those conditions. And then Euclid notice that if you have two conditions and the line should go through 2 points, you get a unique straight line. That's a Gromov-Witten variant. And then you might want to do the same thing with higher degree polynomials. So you might want to do it with conics, cubics, and so on. And the first problem you get is, of course, this conic here is empty. So you might want to switch to complex numbers. You notice that's fine. Euclid's theorem works just fine. So I can now work with complex lines. So I take a complex solution to this equation. That's a one-dimensional complex line, so two real dimensions. And there's a unique one through any 2 points. So from now on, we're going to work with complex numbers. And this isn't so crucial, but actually we can express everything compactly. So we don't have to deal with non-compact spaces. So every line, every complex line, here's our complex line down here, can be compactified by adding a point at infinity to give you the Riemann sphere. This is the holographic projection, which takes any point on this sphere to a point in the plane, except the point at the top, which goes out to infinity. And similarly, you can compactify the plane, or the complex plane that we're working in, by adding a point at infinity for every single complex direction. But it's not so important to understand it. The point is that everything can be phrased in terms of a compact geometry. So now we can go to plane conics. These are also spheres, like that Riemann sphere. So our complex curves are one-dimensional complex objects. Two real-dimensional objects are what we call complex curves. So these are also spheres in this case. And so the real conics that you're more familiar with are the sections, the real sections of these spheres. You get the conic section. So again, we have 6 parameters. We divide by scale. We have 5 parameters, so we can notice 5 conditions and count. Apparently it was Apollonius who did that. And we have 1 conic through 5 generic points. Okay, and then we can go to cubics. So we've seen that already today. Here's a picture of a cubic. So this isn't like y equals x cubed. This is like y squared equals x cubed. And another cubic. These are the real pictures. The complex points, so what we're the complex curves in the complex plane, they're tori, and you see, so the way to go from this picture to this picture is that these curves here, again, get compactified in infinity, so these go off to infinity, and you put your one extra point in, and this just becomes a circle here, and the same here. And those are the real slices drawn on this picture. Okay, but so really it's these we're interested in, these complex curves, but we often just draw the real curves. And some of these tori, let me go back on stage. As I vary the cubic equation, these smooth curves might become singular. So this red curve here might pinch down to a single point, and you get this picture here. So you have this singular point here. And this guy is no longer a torus, but really it's some kind of sphere. It's not an embedded sphere. But this sphere here maps to this torus by just taking 2 points here and squashing them down to 1 point. And that's a holomorphic map, in fact, an algebraic map. And so you could count cubics, or you could count also rational cubics. So these are so-called rational curves, the curves which look like spheres. So this, let me go back here. This looks like a torus, not a sphere in any sense, but this guy it looks like a non-inverted sphere. And one could count those radical cubics and this alarming looking fellow here. And the answer is 12. Okay, so we're up to 1850 now. And then you can carry on, you can also do quartets. So there's a genus 3 curves, so the complex curve has a number associated to it, the genus is the number of holes. And again, you could do, for some quartets, they become singular and you get these nodes. And by opening up these nodes, you end up again with a sphere, and you can count those guys. And Zoyton did that. And you get this number 620. And there you get stuck. So this is really hard, and it gets harder and harder as the numbers go up, and you really get stuck. And then the situation completely changed in the 90s with new ideas coming from symplectic geometry and physics. So these are Gromov and Witten. Gromov-Witten invariants. The point of view completely changed. This rather algebraic problem became an infinite dimensional problem, and there was a lot more flexibility in the setup, and there was a way evolved for how to count holomorphic maps of complex curves into some target, which so far for us has been the plan. And this much more flexible point of view led to immediate progress, even though that flexible point of view has now been rephrased entirely within algebraic geometry, and in some sense could have been carried out many years before. The change in point of view was crucial. And the link to physics has been an enormous source of progress. And the link to physics is that these maps of curves are traced out by strings moving through space. I have a dreadful picture here. So this is meant to be some string moving through some space. So time sort of runs left to right. And as it runs through space, it might start as a point and then get bigger and then split into two and so on. And it was drawn long and thin because what you're supposed to think of is that the classical equations and string theory, as I understand, ask for this object to minimize area in our target space. And for that reason, it ends up being a holomorphic map, and so an object which Euclid and Apollonius and so on. So, in fact, it turns out if you're working with a plane, it's really algebraic. It's really one of the things I've discussed. And the reason I'm drawing long and thin is that area then becomes approximated by length, and so this is more familiar. As the string becomes something like a particle, becomes very small, this becomes something like a geodesic, which is maybe more familiar. Okay, and this new point of view led to immediate progress. Almost immediately, Kontsevich just solved the general problem. So it took us, whatever, 1,000 years, 2,000 years to get up to here. And then this is the general answer. So a recursion for all those numbers. D was the degree, so we had lines, conics, cubics, quartics, and so on. This was how far we got, and then these are the numbers that come. So that was, if you remember, I was always dealing with spheres, the genus 0 guys. And then you might wonder whether higher genus Gromov-Witten invariants can be computed. This turns out to be much harder, a much more nonlinear problem. As an indication, you can study the Gromov-Witten theory of a point. So that's the number of curves in a point. But that's just maps from curves to points. There's only one for the sphere, but for higher genus curves, there are whole families of different complex structures you can put on these curves. And so this becomes the study of complex structures on curves, and it becomes, you end up doing various integrals over modular spaces of curves. And Witten formulated conjecture with sort of a proof by Kontsevich in 1992, and then a more complete proof by Kunkov and Pandharipande in 2001. So it takes just understanding curves in a point takes 3 field medalists in a play research award. This is a very nonlinear, difficult problem. And this sort of highlights where Gromov-Witten theory has gone. So if you don't know anything about Gromov-Witten theory, we're not really interested in the number of conics through 5 points. The interest in the subject is more the answers they produce. So in this case, what you end up with, and in other cases, what you end up with is extremely interesting numbers. When you put them all together in various, package them in various generating functions, you get various links to number theory, representation theory, and in special functions. You get solutions of integral differential equations. And in many ways, that's the interest in the theory. And then, if you want to study curves in curves, maps of curves to curves, that was done by Pandharipande, 2003. Gromf-Witten theory of surfaces is a little different. There's been some progress due to Taubes. We're beginning to understand Gromf-Witten theory of surfaces, but mainly from a three-dimensional point of view. So it's threefold that we're interested in, a sort of key in physics, in string theory, and this is where the main interest lies. So here I'm taking the target to, instead of being the plane, I set the target to be some complex dimensional manifold. And it's here that the big breakthrough that I'm supposed to tell you about is this MNOP conjecture of 2003. And the reason I say this is often in this subject breakthroughs come from physics, and we're all very insecure in the subject of that. Physicists tell us what to do all the time. This one actually came from mathematicians. Okay, so here they are, these are MNOP, and time index. So they're Malik, cross up the Kukoff, Pandharipande. And the MNOP conjecture is a statement about two different ways of counting curves. So there's this Gromov-Witten theory, which counts holomorphic maps from a curve into some complex space. And there's another way of describing a complex curve, which is you could have some curve which is the zeros of some holomorphic equation. So these are two ways of describing curves. And this leads to something called stable pair theory. So these are like parameterized curves and these are unparameterized curves. This is a very nonlinear situation, as we've discussed, almost impossible to compute. This is a much more linear situation because you can add equations, essentially. And the MNOP conjecture states that the invariance you get on this side, so GW, and the invariance you get on this side, with P for pairs, are equal. But equal is a very complicated thing in the subject. So it looks like this. So they're not equal in a very simple way. So these are the Gromov-Witten invariants. So I've fixed my three-dimensional space. It's simpler if it satisfies something called the Calabi-Yau condition. We don't worry about that. And I fix a degree. So this is the homology curve of the curve. This is how many times the curve winds round the space or something. This is like the degree of my polynomial earlier in the talk. And I get this Gromov-Witten invariant counting curves, and that dot there means I use disconnected curves, don't worry about that. And I form a generating function. And similarly, I have stable pair invariants doing a very similar thing, counting curves described by equations instead of by maths. And I form a generating function there. And then remarkably, I substitute q as minus e to the IU, and they become equal. Okay, so you're not supposed to understand this formula. This is meant to be magic. It means you can't really identify one number on one side without knowing all the numbers on the other side. There's some analytic continuation going on here. This is some function sort of expanded around q equals 0, and this one's expanded around q is minus 1, u is 0. And it doesn't even appear to make any sense because this is a complex change of parameters. But it does because this right-hand side is also conjectured by MNOP to be the Lorentz expansion of a rational function invariant under q goes to 1 over q, which is complex conjugation of e to the IU. So this, when you make the substitution, this should still be a real function. Okay, so there's an example. So this Lorentz expansion, these could be stable pair invariants here, and we don't have this q goes to 1 over q symmetry at that level, but this is a Lorentz expansion of a function which does have that symmetry. If you put q inverse in here, multiply top and bottom by q squared, you'll get the same function. Okay, so this is a crazy formula, which is very hard to understand. And you should just think of it as saying that the two sets of invariants contain the same information. And the theorem for which Rahul's receiving the Clay Research Award is a proof of this conjecture for most Calabi-Yau threefolds, most in some technical sense, with his student Aaron Dixon. And very briefly, the scheme of the proof is roughly you degenerate your target space into a union of simpler pieces. So you do a bunch of geometric moves like this. And then, roughly speaking, you say curves here can be, you can equate that to counting curves in x2 and curves in x1, which meet it with appropriate boundary conditions along S, where S is some surface. So if you understand curves in these pieces, plus some boundary conditions, then you might understand curves here. So, roughly speaking, what you do, I haven't read it all 250 pages, according to the introduction. You have to soup up this MNOP conjecture to apply to pairs, so like a Calabi-Yau threefold in the surface, and you have to soup up the MNOP conjecture to apply to various more complicated geometries, descendants, insertions, and so forth. And you have to conjecture that these two sets of invariants are equal with all those extra decorations as well. And then you want to prove that MNOP conjecture. But what you can do now is you can take these x's and s's to be simpler varieties. So you're going to degenerate your x until the pieces are rather simpler. You're going to have many more decorations. You're going to have to prove a worse conjecture for those pieces. But you can take those pieces to be simpler. So let's take them to be something called toric varieties. Those are varieties with an enormous symmetry. They have a symmetry group, the invertible complex numbers cubed acting on them with isolated fixed points. And using this symmetry, you can localize all the information to the fixed points of this symmetry group. Essentially, what goes on away from those fixed points is completely uniform and symmetric. Homogeneous, that's what I mean. And so you try and prove this souped-up MNOP conjecture for these toric varieties by localizing all information to these fixed points, and you get some enormous combinatorial mess, which is then solved, and geometrically, not combinatorially. You don't just get combinatorial identity that's in a book. By MOOP, so this is the same theme with a Blomkopf replacing the Krasov. And then with descendants as well, even more souped up to really prove the whole conjecture by Pandharipande and fixed. That's the rough idea. Last slide. So I just want to say something about Rahul's kind of approach to mathematics. So algebraic geometry is a big venerable subject. It's desperately abstract and old, and that's the way it's evolved. Everyone in the subject wants to be a big theory builder and prove everything by abstract thought and abstract, just sort of pure thought and abstract nonsense. Rahul's not like that at all. And he works essentially by, initially at least, by doing a huge amount of examples. So it's very hard to do examples in algebraic geometry. It's a 1,000-year-old subject, but it's to be computed. But he introduces new techniques. He's incredible at examples. And then, as he does the examples, of course, new theory emerges, new phenomena emerges, and then he produces all the abstract thought and all the new theories as well. But he has this incredible way with examples that mean, as his friend and collaborator Jim Bryan says, he's just never stuck. Unlike the rest of us in the field, we're always stuck. He's never stuck. There's always another example to compute, and that always leads to something interesting. And so this picture is supposed to give you some kind of insight into his mathematical philosophy or something. This is his two graduate students, Pixton and Yanni Kuko, when they finished, presented him with this. If you're cultured, you'll know this is the wrong picture. So this is another of Arnold Schwarzenegger's creations, is the Predator. This is the Terminator. And the phrase is, if it bleeds, we can kill it.
Thank you very much for that, Richard. And I'm going to call on Landon Clay to formally present the Clay Research Award to Rahul Approach.
Now, it's a great pleasure to lift you. Why don't you give it to him? It's heavy. All right. That's a symbol of the CMI. What represents, I'll leave it to the mathematicians, but it is It's been the symbol, and we are very proud of it. We're very proud of you.